The topic, of course, the last topic we're covering is life and the cosmos. We're actually coming to the final step. We've got a pretty long, extensive journey through the universe. For a grand overview, some philosophical comments in this. And basically what we've been, well, hopefully what you've been impressed by is the vastness of the universe, the size. Makes us feel kind of small and insignificant. All the images of the Hubble Ultra Deep Field reveal over 100 billion galaxies up there. Galaxies, I'm talking about not 100 billion stars. Each one of those galaxies is 100 billion or 200 billion, maybe even 300 billion stars. And we can see the observable universe, we can see up to 14 billion light years in all directions. And this is just part of the universe we can see. We now think that the universe maybe extends beyond what we can see. Just the light that from that part has not come here yet. It will in the future. And so we kind of lonely here. So we're going to look at this possibility that there may be somebody else down there. This is the topic of today's class. But basically, I particularly am very impressed how human beings, people like you and me, have worked over the centuries to figure all this out. So, we're pretty clever for a bunch who was just apes a couple of million years ago. We were descended from apes, we'll see today. And only recently figured out how to walk upright. Recently, I'm talking about the general picture. Okay, the general picture, the time frame that we learned to walk, humans, well, that's a very short amount of time ago when you compare it to the life of the whole universe. So what field of astronomy now is the most exciting is what we're going to be talking about right now, exoplanets, the search for planets orbiting other stars, not our sun, but orbiting other suns. And 20 years ago, we weren't sure that there were any other planets besides the planets in our solar system. But now we've discovered, using new technology, thousands of other planets. Just about every star that's out there has planets orbiting it. Now, we can only examine stars that are pretty close. We can't examine everyone. But just looking at the stars that are pretty close, and we'll see which stars I'm talking about. So, whereas the ancients thought that universe was just the solar system and a sphere of bright lights rotating around us, we were in the middle, we eventually understood the true scope of the Milky Way galaxy. With its 700 billion stars, many of which probably have one or more planets, just like ours. Many of them have planets. We already found that out. So we know one place for sure, where intelligent life is, and where life was developed and how it came about. This is it, Earth. We don't know if there is any life, much less intelligent life, anywhere else. So we're going to make some, a little bit later, we're going to make some guesses. Now, life being generated spontaneously from non-living matter, how does that work, by the way? How do you take atoms and make them living things? Now, even if you think that this happens like 1 in a billion shot, there's a billion places where it could have happened. So it may have happened somewhere else in this universe. There are billions of worlds in our galaxy alone. And when you combine this infinitesimal odds, very small odds of life coming together from non-living matter with the impossibly large numbers of places where it could happen, you get certain probabilities for the unlikeliest things to happen. So what is necessary for life to exist? Well, number one, we know that these 5 pieces of matter, carbon, hydrogen, oxygen, nitrogen. But what else is necessary is water. We know for a fact, almost for 100% certainty, that life developed in water, because it could not have developed any other way, because the Earth was, the surface of the Earth was just a ball of fire. And so it must have developed underneath the ground where we had water. So first of all, what are the conditions for life to exist? Well, water is one of them. If we think about life on Earth, we know liquid water was absolutely crucial. This was the medium in which the first organic molecules underwent endless chemical reactions until eventually stumbling upon chemical reactions which created a self-replicating structure by chance. So this is, we think, the way we think life developed. These atoms underwent endless chemical reactions until they came upon something they created that had the ability to make a duplicate of itself. And just by chance, this happened. That's what we think. Anyway, we don't have all the answers for this, by the way. We have some of the answers. So when we look at stars, and what we want to see, first of all, something more basic. Are there planets orbiting it? And how do we know that? And maybe this planet have the ability to have life on it. So first of all, we know the liquid water must be there. So a planet must be somewhere what we call the habitable zone of a star. In other words, far enough so that it's cool enough for water to form. If it's too close, water boils away. If it's too far, water freezes. You have to have this, sometimes it's called the Goldilocks zone. And for every star, this will be different, the Goldilocks zone, where water can exist. In other words, the surface temperature should be between 0 and 100 degrees Celsius, freezing and boiling points of water. Further away, it's too cold. Closer, it's too hot. This is called the habitable zone. This is the range of distances, all the blue, green stuff here, where any planet that's orbiting the sun in this area has the ability to do water. So it doesn't mean it has life, but it could. It could have life because it has water. So this is one of the things we argue. Water must be on the surface of the planet. So far, if we're looking at all the planets in our solar system and all the moons, we have not found actual water on any of them. And there's lots of moons. I know the planets don't have water, but the moons don't even have water. But they show signs of having had water in the past, including Mars. Looks like it had water. So life could have developed. I'm not talking about people, Martians walking around, but I'm talking about microbes. One-celled life maybe. So particularly these two moons, Jupiter's moon Europa and Enceladus, Saturn's moon, they seem to have signs of having had water in the past. And both of these have a very thin atmosphere. So some kind of life could have developed. I mean, there's no way any life that resembles us is there. But again, maybe some microbes are there. Right now, we haven't found any anywhere. Now, our solar system generates a lot of heat from the inside, enough heat to melt ice and get liquid water. So Jupiter's moon gets heat from Jupiter itself, because Jupiter is almost a star. We know a reasonable certainty that a number of these worlds contains oceans of liquid water, mostly Europa and Enceladus, underneath the surface. They at least contain it. And it looks like it had, in the past, it was on the surface. Maybe only 1 in a billion planets with basic life forms will produce complex life that can reach technology, like us. People who create things and understand things. Maybe 1 in a billion, but if there's a 1 in a billion, if that's the chance, and there are billions of worlds like this, then there should be some kind of intelligent life that we should be able to communicate with. Now, as to how this simple life that we, that's an amoeba, a cell, how does it evolve into intelligent life like us? That's another story altogether. We're going to briefly look at it, but that's a very tough story to figure out. It might be the case that only like 1 in a billion does a world with basic forms of life produce a civilization capable of creating technology. But if that's true, then there should be intelligence out there. So how many such civilizations exist in our galaxy? 5,000, or none maybe. Maybe we are truly alone. So we're going to look at, in a bit, we're going to look at the odds. Because there's a fellow, they came up and tried to look at the odds. But that's going to be a couple of slides down. Now, first of all, we're going to look at the search for planets. All right. The first, they call exoplanets. Planets that are orbiting other stars than our sun, not our sun. The first such planet, exoplanet, was discovered in 1992. And up to about the year 2000, that was the only one that we knew was out there. Now, obviously, we knew Earth and all the planets in our solar system, but I'm talking about exoplanets. One. But since then, beginning in the year 2000, new technology, we found thousands of planets out there, thousands of planets. We're going to look at this technology. But basically, when we're looking for planets, we actually can only look mostly in this area here. Okay? We can't look any further away to find a planet. You know, it's too hard to find a planet. Now, just recently, there's a new method of doing it, and we were able to find a planet that's further away from us. You'll see it in the next slide. That's further away from us than, this is approximately, tells you here, 300 light years all around in either direction. We can look at 300 light years. There's plenty of stars out there within that range, and we can actually find planets circling them. I'm going to show you a little bit later how. And those planets, we can figure out a lot of things about them, like how big they are, how far away they are from their sun. That means whether they are in a habitable zone. So astronomers discovered one of the most distant planets, known as a gas giant, about 13,000 light years. So even though we can find many here, further away gets tougher. There was a giant star 13,000 light years from Earth. And this is recent, the last couple of years. The planet was discovered using a technique called micro-lensing, using a Spitzer Space Telescope and an optical gravitational lensing experiment. It's called OGLE, optical gravitational lensing experiment. They found a planet this far away, which is amazing. Here it is. All right. Usually all the planets have been in this area here where the red is, but we found a few further away. And this planet that I just talked about is right over here. So this is a little chart that shows you how many planets we knew were out there besides us. Beginning in the early 1990s, this is how many. Almost none. 1, 2, 3, 4. And again, around the year 2008, 9, 10, new technology enabled us to find more planets. And now we found this many planets in the last couple of years. We're discovering them all the time. So this is as of the year 2017. All the planets that have been found. So these are called exoplanets, alien worlds, planets orbiting other stars. The first was discovered in 1992, and now we have thousands of them. And many more thousands are awaiting confirmation. Most of these exoplanets are giants. They got to be big for us to see them, to detect them. We can't see them, but we can detect them. So they're far more massive than the Earth and likely to have very thick atmospheres like Neptune or Jupiter. That's what they appear to be more like, not like Earth. Though some are different. The diversity of these planets is stunning. Some are hot, some are cold, some are big, some are little. Some in solar systems that are so compact they can fit 5 planets inside the orbit of Mercury. In other words, their star is so small, but it's a star providing heat, and 5 planets can be closer than Mercury is. And also they can be very far away. So we now think that most stars in the galaxy have planets. Now this is, for example, a little show of what I mentioned before, the habitable zone. And this is our sun in the middle here. And we can see this Mercury, Venus, you know, they're inside the hospitable zone. They're not in the hospitable zone. They're too close. It's too hot for them, all right, to have water on them. Earth is right smack in the middle right now. Mars is just outside. And some people actually count Mars as being in a hospitable zone. It's so close. And we'll see a bit later, a fellow named of Drake assumes that Mars is actually in the hospitable zone. And of course, all of these are outside. They're too far out. So this is called astrobiology, the possibility of life in the universe. So you can see over here, what happens is, well, let's go back to the other slide. Oops. You notice that the hospitable zone for our sun is right here, but if we went to a star that's a little larger than our sun, it would be further away. It would go like this. And you can see in this slide how it goes away. This is our sun over here, and this is Earth over here. Mars is right over here. But going to other stars, and there are planets now that we have found, and most of these planets are named Kepler one thing or other, Kepler 22b, Kepler 62, and that's because the space probes that look for use the Kepler space telescope to try to find. Here's some stars. Here's some planets that are close to their star. Okay, Gliese 667, Gliese 581. These are close. They're all in the hospitable zone of their star, which is smaller than our sun. So this diagram shows where hospitable zone is located for different types of stars. Estimates range as high as 8 billion Earth-sized planets in the habitable zones of their stars in our Milky Way galaxy. So we estimate there's 8 billion Earth-sized planets. So as I mentioned, this search utilizes the Kepler Space Telescope. I don't know why this was launched in 2009. And this thing got messed up a little bit. Anyway, it says Kepler mission. The Kepler mission determines the frequency of Earth-sized planets and larger planets in the habitable zone of sun-like stars. And what does it find about them? It finds their size, approximate size, and orbital period, how long it takes the planet to go around their sun. And to do this, it needs to use radio waves, not visible light. Because visible light, you look at things far away, it gets absorbed, it gets scattered. But radio waves don't. Radio waves travel through anything. But to have radio waves, these telescopes that we have on Earth to receive this information must be tremendously large. They're like, a mile apart, parts of them, miles apart. So I already mentioned this. This is called the circumstellar habitable zone. The distance around a star where water can be. It's called the habitable zone. Now, for the sun at present, the circumstellar habitable zone ranges from 0.97 AU to 1.37 AU. So on Earth, we're 1 AU. That means we're pretty close to the edge of the habitable zone right now. And Mars is just outside the habitable zone. So here you have some examples for very hot stars, like over here, the hot star. The habitable zone is further out. For sun-like stars, the habitable zone is in. For cooler stars, the habitable zone is right close to the star. And this probably contains the most interesting planets that we've found, because there are many planets within that zone. Okay, so let me show you this little simulation here about the habitable zone. So this is, in some years we do this experiment as the last experiment, but this is done better if if you do it in class as a group. So right now, this is Earth, right? This is our sun, Mercury, Venus. They're inside the habitable zone. The Earth is over here. Mars is outside. And we can, if we take Earth out, you can see a couple of things about Earth. It won't be an habitable zone anymore. Okay. But let's put Earth back here for a time. What I'd like to do is run a simulation of the universe and look into the future. So right here we can change the mass of the sun. Right now it's set at 1 solar mass, and the distance is about 1 astronomical unit. And if we run the simulation for time, this is what it looks like. So what you're going to do here, look what happens to our sun, and look what happens to the habitable zone in the future. This is where we are right now, okay, about right now. And this is going to happen to us in the future, what's happening here. The habitable zone is going to move out because the sun is going to actually get hotter and expand. So we're too close now. And you can look at the sun over here. It's on the HR diagram. As it gets to the end, it goes off the diagram because it becomes a red giant. And then, boom, it becomes a white dwarf, and that's it for us here. But that's going to happen in about 5 billion years. Now, okay. So we could in fact change this to another star and see if the star was, let's say, smaller than us, then we would be outside the habitable zone. If this star was smaller than our sun, smaller, less massive, I mean, okay, we would be outside the habitable zone right now. Okay, let's go back to our PowerPoint. So this, too bad we didn't have time to do this. This is actually a pretty fun simulation, I think. So not only does our sun have a habitable zone, but our whole galaxy has a habitable zone, which means stars that are here have better chances of having life in Earth-like planets in the habitable zone. If you get too close, it gets too hot. There's too many stars there, too much radiation. You get too far away, you don't have enough heavy metals, heavy atoms. Right around where we are, this is our sun. It's in this area, orbiting around, and that's just the right area for, well, for us, I guess. Like I said, inside too much radiation. This is 2.5 days, 4 days, 6 days, 9 days. Days, I'm talking about days, not years. Compared that to Earth, where Mercury orbits in 88 days, Venus in 225, Earth in 365, Mars in 686 days, because they're far away. But these are close to the planet. The planet, close to the sun. This star is, in fact, a small star, much smaller than our own star. And 3 of the planets, E, F, and G, are within the habitable zone, the Goldilocks zone. A, B, and C are too close or too hot, and there's another planet outside. Okay. So this is a little film about this TRAPPIST system. Give you a little more information.
All right, everyone, here is one of your most asked for videos. Everything you could want to know about the TRAPPIST system. And I can see why there is so much interest. It is such a unique system compared to anything else that we know of. An entire solar system contained well within the distance of Mercury and the Sun. It is one of the closest places to us that could harbor alien life outside the solar system, it being only 40 light years away from us. That means we won't be visiting it anytime soon. But with improved technology from the James Webb Space Telescope, we will be able to gain an insight into another solar system like never before. I'm Alex McColgan, and you're watching Astrum, and together we will go through the TRAPPIST system and see why it is so special. Let's begin at the heart of the TRAPPIST system, TRAPPIST-1 itself, the ultra-cool red dwarf star, a star which is just a little bit bigger than Jupiter, but a lot more massive. Red dwarf stars are the most common type of star in the galaxy. Even our closest neighbor, Proxima Centauri, is a red dwarf, as is 50 of the closest 60 stars to us. Being so cool means they are very long-lived. Stellar models suggest they could exist for trillions of years, which is far more than the current age of the universe. Although there are many known red dwarfs with exoplanets around them, typically red dwarfs are dubious candidates to have life. This is because the Goldilocks zone, or the distance from the star where water could theoretically pool on the planet's surface, is extremely close to the parent star, meaning any exoplanets orbiting in this zone are likely tidally locked. This means one side of the planet would always be facing the star, and the other side would be in perpetual night. The night side would be cold enough for gases in the atmosphere to freeze. Also, red dwarf stars are often flare stars, or stars that can have their brightness increase very rapidly to magnitudes brighter than they are normally. This is similar in a way to a solar flare on our sun, but on a much grander scale.
Okay, so we're going to move on from that. So let's first ask a question here. Even if there's a low chance that any one planet has life on it, there may be many advanced civilizations. Why? Well, because there are so many stars. That's why. A is the right answer. There are billions and billions of stars. So even there's a low chance that any one planet has life on it, but you're talking about billions of planets, one's bound to have life on it. Okay, so that brings us to life. What is life? Well, it's a complex biochemical process that does what? Draws energy from its environment to survive. One thing. So it draws energy from its environment and reproduces. In other words, makes copies of itself. This is what life is. Okay. Now, Earth's secondary atmosphere, the original atmosphere that the Earth had when it came about, is gone. It has a secondary atmosphere. It was formed in part by carbon dioxide and water vapor. It was a product of volcanism. In other words, volcanoes ejected stuff to the Earth's surface, and that became, some of that stuff became the atmosphere of Earth at that time. Nothing resembling what it is now. It was a completely different atmosphere. But this vapor formed oceans which turned into rain. Now, cometary impacts may have had an additional source for water. Comets could have had water on them and brought it here from somewhere else, as well as adding methane, and ammonia. Molecules rained out of the atmosphere and into our oceans. So this is what the early Earth looked like. They had volcanoes, stuff coming out of the volcanoes, replacing the atmosphere that was there. So you can imagine that ancient Earth was a tough place to live. No life could have had a chance to come about here. Yet, we know that life took a hold within a few 100 million years after it was formed. We know that the Earth was formed about 4.5 billion years ago, and by 4 billion years ago, life was already on the planet. Some sort of life, not humans walking around, but microbes swimming around. So we think that life began deep in the ocean, and if you look at a calendar year, the birth of the universe. Remember, we had that calendar. We were to compress everything that happened in the universe to 1 year, where the Big Bang happened in January 1st, and today is December 29th, 59 seconds. So we think that life began deep in the ocean on September 2nd in this imaginary year. Mammals first appeared later, but 2 million years ago, 200 million years ago, December 26th. So life appearing September 2nd, and mammals, things that actually run around, just 200 million years ago, December 26th. And don't forget, today is December 31st. On December 31st at 7 p.m., we had a parting of ways with our closest relatives, the chimpanzees. So let's take a look at this in the next slide. Why of all the 5 billion species that have ever lived on Earth, did we alone evolve into civilization today? In other words, at this time, 5 billion different types of microbial life existed on Earth. And we alone evolved into humans. All right, so here is that calendar we've been talking about. January 1st, the Big Bang. And December 31st, today. Every month is 1 billion years. Every day is 40 million years. So let's see. January 13th, on this calendar, galaxies began to form. August 21st, or 31st, our sun was born, sort of right in mid-year. September 2nd, the first cell came about. Now we jump way over to December 31st, 11 p.m. That's when humans emerged. So humans, when you look at the whole life of the universe, emerged very recently on this planet. Humans, meaning people who walk and talk and can make tools. And December 31st, 1146, all of recorded history within that last 4 minutes on this calendar. Now, as I mentioned, mammals first appeared 200 million years ago, December 26th, and December 31st, 7 p.m., we had a parting of ways with our ancestors, the chimpanzees. We come from the same. So Earth's atmosphere in the oceans, okay, so this is the slide I had earlier. Earth's atmosphere appeared before the sun was fully formed. The atmosphere originally was just hydrogen and helium. But when the sun was formed, it swept away the original atmosphere, and a new atmosphere was formed. Now, this new atmosphere developed in stages. Hot gases escaped from volcanoes, so they contributed to the atmosphere. Free oxygen occurs as a result of photosynthesis by various types of bacteria. So oxygen was emitted by, in fact, the life that was formed. Ozone began to accumulate in the upper atmosphere. Water vapor condensed to form oceans. Rain fell from the sky, that is. And this is how we think the original life formed. Deep in these oceans. This is called the lost city of life, a place where this city being underwater, geyser, this underwater geyser, discovered in 1978. It's in the floor of the Atlantic Ocean, shows a collection of limestone towers known as the Lost City. We found life forms that were surviving from the Earth's geothermal heat, from the heat generated by the inside of the Earth. Various hydrothermal vents of this type are suggested to be the first living organisms on the ancient planet. But who created these? Okay, so this is how we think life got started, where it was able to actually combine non-living to living things. Now, there was no life on Earth then, so nature created life. On September 2nd of this cosmic year, this is where we think life began, from a single cell. So the first cell was formed, and from that single cell, everything else came about eventually. So life most likely began in the oceans about 3.5 billion years ago. These life forms are called extremophiles, and that means they could survive almost anything, even in free space. They were so hardy. these life forms. They would have thrived around freezing, severe, or high temperature conditions. The number of new, so life was formed, but this one-celled life remained for about 4 billion years. Didn't do anything, didn't change much. One-celled life. But something strange happened about 500 million years ago. These cells started reproducing very rapidly. Now, living organisms extract energy from their environment, and humans extract energy mainly by eating and breathing. This is how you get energy from your environment. Plants extract energy directly from the sun. They absorb sunlight, and through photosynthesis, they emit oxygen. So what is life? How do you define something is life? First of all, the ability to generate and use energy flows, as we just showed. The ability to reproduce, the ability to make multiple copies of itself. And very important, to adapt, the ability over time to slowly change in ways that enable you to fit into your environment. In other words, if your environment changes and you can no longer generate energy very well from the environment, you change. So you could do it. So reproduction is the ability of living organisms to make multiple copies of themselves. Adaptation is the ability of living species to change over time as to find new ways to extract energy from their environment. Adaptation allows organisms to keep extracting energy from their environments, even if their environments change, because the organisms change themselves. So this is the way we define what is life. So this adaptation is the ability unique to living organisms to change over time so as to fit better into their surroundings. This is how you could say it. Now we could, have a whole course on this.